This is AI Makerspace, and this is officially our first session. So this space is meant to be a sort of an informal set of office hours in which we're just gonna sit down and code something. Ideally, the topics that we're going to be covering are going to be related to the day-to-day research that we do. The hosts are going to be Mithun and myself. And this is meant to be like a fun hour in which we hopefully achieve the goal that we set. But the topic is not well. The list of topics is not fixed. So depending on what of the demand. So today's first day, but probably it'll pick up later next week. If people start asking about I want to I want to fine tune an LLM, or I want to learn how to code agents. So we're open to sign one of those sessions and try to figure it out together. So this is meant to be a conversation. Feel free to interrupt me and then ask questions. And I'm going to start coding. So today I'm going to be the host. Nathan is going to be assisting me, my assistant Nathan. But next week is going to be the other way around. So today's topic is going to be about training PyTorch code in multi-node environments. And what does it mean? Much basically, when you're training a deep neural network, say like an LLM or a huge condition model, it is common that it doesn't fit in a single GPU, or if we have like a consumer grade GPU with a gaming video card, it might not have enough VRAM, or we might be using a model that has 70 billion parameters, and it won't fit likely in an A100 or a V100. So we have to make use of multiple GPUs in order to train stuff. Or sometimes we want to do it faster. Maybe we have enough hardware there such that we can finish our training pretty quickly if we leverage all of it. So conceptually, it's simple. It's just splitting the task into multiple partitions that are directed to the GPU. But in practice, it's actually quite difficult to do because it's very error prone. It depends a lot on what is the topology of the computers that you have. If you have a single computer or a server that has 4 GPUs, or if you have a cluster that has multiple nodes that have 1 GPU each, depending on that, you need to change the configuration. And then how do you access it? Maybe it's a dedicated GPU from your lab. Maybe it's the HPC. You'll need different means to access it. So us being in the university community, we have access to the HPC, and the HPC has some clusters that have GPUs. So these GPUs are not latest, nonetheless they are really useful. And one of the strengths of it is that we can use them simultaneously. So we can run that has 5 or 6 or however many they are available. If we get an allocation, we are able to use them. So what you and I are going to do together is that we are going to take ResNet. ResNet is a deep convolutional neural network designed for image
Enrique,
classification.
are you planning to share your screen?
Yes.
Okay, you do that. Okay, you're not right
yes.
now. Just want to let you know.
No, I'm not writing it. I'm describing what we're going to do. So we're going to take ResNet. ResNet is a neural network that is not very large, but we can split the job into separate nodes, and we're going to train it for one epoch using imagenet. Imagenet is a dataset that contains about 1.2 million images for training. We're not going to focus on evaluating it or on doing inference or predictions. We just want to let it run and make sure that it's using the GPUs on different computers. So physically separate computers that have independent GPUs, seeing that they're being utilized at a 100%. So I'm going to start sharing my screen now. And we're going to do that using the HPC. I'm not doing this by myself. So instead, I am doing a potpourri of code that I found online. And hopefully it's going to work. But we're going to touch multiple aspects, such as coding with PyTorch, then uploading stuff into the HPC, running into the HPC. We're going to speak about the caveats of running on the HPC, how we can manage our way around it. And by that mean, like, we might be kicked out when our time is up, or if we're using Windfall, if a priority job comes in, and so forth. But we're going to start with this piece of code. ResNet 50 means this is a ResNet architecture and has 50 layers of stacked CNNs.
Can you make it a little bigger, maybe full screen or something?
Yes. Hold on. Does that look better?
Yes.
Okay. So first things first, we need to take this code and we need to write it into a file. And this is going to be as simple as just copying it to VS Code. So VS Code, I'm going to make it bigger as well. Okay, so this is just a copy paste of the code. I'm just going to walk you through what are the steps. So I'm not a computer vision expert, but I do know PyTorch, so I think that I can explain most of it correctly. And with this explanation, you should understand pretty much what this is doing. It is relatively basic in terms of computer vision, so should be simple to understand. First, we need to import our stuff. We're going to make use of PyTorch, as I was mentioning. The Torch Vision is a package that contains utilities to deal with images for computer vision. And concurrently, we're going to use the transformations. So the first thing is that we are going to instantiate a device object. And this device is going to check whether there's an available GPU. And if not, there's a CPU. This is pretty standard. We're going to set our hyperparameters. We're going to train for 1 epoch instead of 10 because we just want to make the point that we're using everything. And we're going to bump up the batch size. So the batch size, and please, like, feel free to interrupt me if something is not clear. What this means is that at each step during training, we're going to take 128 images. We're going to apply those transformations, and then we're going to pass them through the neural network through ResNet. So depending on the GPU, you may have a V100 that has 32 gigs of RAM, or you may have an H100 that has 80 gigs of RAM. The more RAM you have, the more elements you can fit into your batch. So this could be 256, 512, etc. So a good practice of this is that you want to maximize your use of memory and your use of compute. Because if you are spending a lot of time shuffling around data back and forth the GPU, that takes up cycles that you could be using doing training. So it's going to be faster if you can make the batch bigger. There's going to be some point in which no matter how much you can fit into the batch, you're maxing out the GPU. So you can see that whenever we're gonna see it, the utilization plot, it's at 100%, and maybe you can still fit more elements, but it's not going to change the estimated amount of time to train 1 epoch. So learn rate, this is like a standard. Without knowing anything else, we are going to do 0.001. We're going to load a transform utility. What this is doing is that it's going to take images. So images are going to be JPEG files. I'm going to show them to you. And we're going to normalize them to a specific format. What does that mean? We're going to resize them to 256 by 256 pixels. The reason for this is because ResNet is trained to expect input images of this resolution. So even if, say, you have, I don't know, 10 megapixels image, you want to scale it down, or if it's smaller, you want to scale it up. Then it's doing some. To be honest, I'm not sure. Like if these transforms figure out if this is necessary or not, but it's going to flip them horizontally and flip them vertically and rotate them. So this is because sometimes you may have an image that is rotated by a certain angle or might need like to flip around. So this pipeline of composition takes care of it, and it's doing some other stuff, like for example, it's cropping to the middle, and in the end, it's creating a tensor. So that tensor is then normalized. This is just mathematical operations that ensure that no matter what's the input format, so meaning like, is this a color image? Is this a black and white image? Is this a of the specific size? It doesn't matter. It's normalized to the same parameters that ResNet is being trained for. So with that out of the way, we need to load our data set. Something important here is that we need to have the imagenet dataset downloaded. And I did this ahead of time because this is, it's like 120 gigs of individual JPEG images. So it takes a while. So you need to download it. It is freely available on Kaggle. So I'm going to write some notes and I'm going to post them on the Makerspace website such that you can know where to download this data from. But in the end, I had to download it into the HPC. It took about a night of download to do it, so you have to do it ahead of time. So we're going to change this to a directory, and I'm going to type it here. So this is a path relative to our HPC, but it depends. Like if you're sponsored by someone else, you're going to need to change this to whoever is your sponsor, like Niraf or I don't know, Clay Morrison, whoever. And then you just need to dump your files over there. So what this is doing is that we are assuming that we have a directory on the file system that contains images. Whose root is this? And then we're going to transform each of the images through the pipeline that we define here. So far so good, Mithun.
Yeah. Maybe I don't know why they didn't request. I would like to see it a little bit more bigger though. If it's okay with others, I don't care. Yeah.
Okay. So then we need to have a data loader, and we are going to instantiate ResNet. So there's one key aspect here. ResNet is a pre-trained. What that means is that somebody else already did a train loop on top of it on the data set. So we're just loading those weights. And the Torch Vision package, sort of like Hugging Face, but this is native PyTorch, already has it somewhere that we can download it. So then the rest of the code is going to be a send it to the GPU, instantiate the specific loss function, the training algorithm, which is going to be Adam here. So then we're going to step into a standard training loop. So we take for each batch in the data loader, we take the input files, which is a tensor that contains multiple images and the labels for each. We send them to the GPU, both of them. We are initializing our optimizer, and then we are piping them through the model. This is where the actual transformation through the deep neural network happens. The output is going to be a set of tensors that provide a probability for each class. We use the criterion function defined above, the cross entropy loss, to compute the difference between the predictions and the labels. And depending on this loss, so whenever we start, it's going to be higher, but through backpropagation and the backpropagation step, that's going to be reduced each time around, and then we do one optimization step. So in the end, this loop is a train procedure, and we're going to inspect how well it does. So the next step that we have to do is that we need to upload this into the HPC. So I'm going to use the scp command, and I'm going to upload ResNet 50 into So there are multiple ways in which you can do this, but I recommend using directly SSH and SCP or rsync, because it'll make your life easier. So it might be more convenient if you are not used to, or this is your first rodeo with the HPC, but moving around files is easy to do with SSH associated commands. So what I did is that I took this file and I uploaded it somewhere in the HPC. And now I'm going to step into the HPC shell. So I'm going to add in the notes pointers to the way to connect to it. I already have it set up in my computer. That's why it's not asking me for password. But in here, you can see that we have the file that we just uploaded. You can see it here. So I'm going to, I have a directory called Makerspace. And I'm going to move all this. So I was preparing this session before. Then I'm going to move the present file here. Okay. So the next thing that we have to do, say that we want to test this, right? So we have the code there. We think it works, but let's see if it actually works. So a way in which you can do this is that you can request an interactive job, which is going to give you a shell on the node that actually executes something. So we're going to ask for, we're going to see what are the parameters. So we want one node. We're going to request a CPUs, and we want the GPU, and we have the, we want 1 hour. Oh yes, I need to specify how many nodes do I want. I want 1 node. So it's going to wait for a little bit. Another way in which we can see how busy this is, we can SSH into the HPC and see the nodes busy command. We see that it's quite busy. Puma is quite busy. Let's see Ocelot. So this one. So what you're seeing here is that we have multiple nodes where each has 2 GPUs, or sometimes 4. And here we can see that there's a node that has, there are multiple nodes that have 2 GPUs available. So what we're going to do here is that we are going to kill this. We're going to change to Ocelot. And we're going to request an interactive session. But we're going to use the Windfall account. It's likely that we're going to get a location faster this way. But while we wait for this, I'm going to show you a file that we're going to use to adapt. I'm going to make this bigger, so hopefully it helps. There's another file that is provided by the PyTorch folks, which explain you how you can parallelize using the distributed data parallel paradigm. What this does is basically you specify how many elements, how many computers you want, and you're going to run the same process on each of those at the same time. One of those is going to be the main node, and the other are going to be other worker nodes. And by configuration, you specify what's the AP address, the main host, which is here master address. So whenever you start it, all the worker processes in the separate nodes try to connect to the main worker process. Once they're all connected, then each of them executes the same thing at the same time, and start distributing the data. So that means that if like your batch size was of 100 images on a single GPU, instead you're going to split it. If you're using two nodes, you're going to split 50 and 50 and send each to each node to compute the forward step. Once it finishes, it's going to do the backward step, and it's going to synchronize the gradients to the master process or the main process. When it does that, then it's going to compute the optimization, and it's going to distribute the new model to the worker processes. So it has some overhead, but whenever you are maximizing the usage of this GPU, it'll excuse me, you'll get some gains. So what we're going to do here is that we are going to adapt this script to use the ResNet model here. So I'm going to copy elements from here into multi-GPU. So since I'm not sure exactly what time we're going to get this, so what I'm going to do this here is we're going to request another one in Puma as well. And
Enrique, don't take Windfall, just take my default so you get it faster.
oh, actually, so the reason why I do that is that it is sometimes faster with Windfall because so Puma has some buy-in nodes that are not available with the standard one. But yeah,
I have buy-in nodes, so you will.
Oh, perfect. And if you see where I'm doing a mistake, let me know.
He doesn't like you on my account. I don't know why it's complaining of.
So selecting here. Okay. Let's see if we can get the one. How did? Oh yes, I see. I see what was going on. This is just G. One. There we go. Okay, so we're waiting for the allocation here. Let's see what happens. But meanwhile, let's start adapting this code. So I'm going to open it in parallel here in multi-GPU. I'm going to comment this out. You're going to see why later. Epoch checkpoint. Yes, so this is important. So we have to copy this here. So in this method, we're loading the individual elements. So we need this here. Then for model, copy this here. Okay, so I don't know why VS Code is insisting in me using indentation. Okay, so train data set goes here. So it's going to move this a little bit to the right. What we're doing here is that we're pasting the elements that we need. So the train data set with the transformations, the ResNet model, learning rate, we're just going to put here 0.001 into this method that loads them. I don't know why it doesn't have self. Okay. So then we prepare the data loader. So here we have string data loader. Change this dataset to word graph. And this, I'm just going to emulate whatever is down. Shuffle here, strew number of workers. I'm going to put 8 because we're going to need it. And in memory, I'm not exactly sure what does this do. But something important is that we need to use the distributed sampler. So this is because of the nature of distributed training. So train the order. Okay.
Can I ask a question?
Yeah.
Why do we need to like decide the number of workers like here? I thought, sorry, go ahead.
Yeah, this is a good question. So this is independent of the GPUs. And I am putting this number because I tried this ahead of time. But basically, what you want to do is that you want to keep the GPUs fed with input data. And as you might remember that there are some transformations going on here. All of this happens on the CPU. So you want to have multiple workers that are opening the JPEG files and applying these transformations and creating the tensors that represent those images while the GPU is working. The issue usually is that GPUs are extremely faster than the CPUs when they're doing their stuff. So one way to keep a pipeline ready with new data is having multiple workers to leverage the multi-threading nature of the CPUs. So at the beginning,
sorry, so if you didn't like specify the number of workers, then that would just like ignore it and then just only like use the rank that's been decided and just wait for that, or like I'm kind of confused with like the difference between rank versus like the number of workers, I guess.
Yes. So rank applies to the allocation that you have on the HPC. So if you have two jobs on the HPC on different nodes, you have rank 0 and 1. And then on each node, you're going to have multiple threads that are doing the CPU work. That is the number of workers. So if you don't specify it, this is going to be 1. And then it's going to stall because the GPU is always sitting waiting for the single core to do its stuff. And this is one of the things that I had to debug ahead of time, and I found that this was a sweet spot.
Thank you.
So then in the main, so let me see all this. Oh yeah, we have something now. So let's hold the thought on multi-GPU. Let's since we already have an allocation on Puma, let's go and see how many GPUs we have. So we have one B100 with 32 gigs. We're currently not using it. What you're seeing here is a shell, and this shell we can do stuff. So in here I have the ResNet 50 function. I have a Conda environment that I set up ahead of time. So I'm just gonna activate it. And I know that Makespace is not Makerspace. That was a typo, and I haven't been able to fix it. But let's see what happens when we run this. It's going to take a little bit because it has, so imagenet has 1.2 million images. So this is I think it's enumerating those files somewhere. Okay, so let's fix this. Okay, so here we're going to use the what's missing. It was missing a directory. It's verified. We have 1 hour of GPU. Okay. So just want to make sure that we are running it end to end. Then we can execute the multi-GPU. So something that you can do when you have an interactive session is that if you see this R5U29N1, this is the node that you have, and you can actually SSH into it. So first you need to get into the SSH, into the HPC basin node, and then you can SSH into it. And here I have another shell on the same session. So we can check if it's working. It's still not using the GPU because it's taking some time to load. But let's just wait for it a little bit. But meanwhile, we adapted this file, and once we verify that this works, we're going to run this other one that has the multi-GPU. So the important part here is that the data loader was substituted with it's augmented using the distributed sampler. And when you read it, you will see that the model itself is wrapped around this DDP class. The DDP class stands for distributed data parallel. And what it does is that PyTorch has hooks in it, such that whenever it's doing the forward and backward passes, it'll distribute the load using the different parallel computing constructs. So it's going to scatter the data, it's going to run it, and then it's going to gather results, unify them, and then scatter the new model, and so forth. So PyTorch already has all of that for us. I'm going to post the link to the explanation of it. It is not trivial, but it works. So, well, what I'm going to do. So let's see. I'm going to Makerspace. Then I'm going to the backup. So in here, I have the same class, and then there is a script called run ResNet. I have it here already. This is the last piece. When you're running it, you want to use a Slurm. Slurm is a way to schedule the tasks on the HPC, and you specify the parameters that you want. So in this case, I create a small bash script that loads Anaconda. So I did this by hand, then activates the Makerspace command environment. you need to fetch the parameters like of what is the actual main node. This comes out of the documentation of PyTorch, so you can feel free to copy and paste it yourself. But when you run it on a multi-node environment, you want to use torch run instead of running Python directly. What is that? It is a torch run is a launcher that is going to warranty that everything orchestrates and configures correctly. Otherwise, you will need to go and do it yourself by hand. It like defines parameters of a rendezvous algorithm, which is I'm not sure exactly what it is, but it coordinates the communication between the processes. So here I'm specifying that we have 2 nodes, so 2 computers, and we're going to have 1 process per computer with 1 GPU. We pass through the environment. What is the IP address or the host of the main node, and we run that training algorithm. We specify what is the batch size, the number of epochs, and how often should we save our stuff. So in here, we can see that it made progress already. It gave us a warning about loading the model. So let's see if we can actually see some change in the GPU. Right. So now you see part of memory is populated already. So it's going to take a little bit more to start training. But meanwhile, what we can do is that we can do sbatch, run ResNet. And this is going to take whatever is here on the node. We specify the parameters of the allocation that we want and execute it. So our job has an ID, and we can see if it's running by running SQ. So I have 2 jobs running right now, the interactive one, and the other one has 2 nodes. It's still scheduled. It hasn't started running. It'll take a little bit, as you see. The important part is that we are going to see the 2 GPUs working at the same time.
Question.
Yeah.
So for when you're like running on like 2 nodes, you're like literally just using the ResNet 50 like code, right? Like, why don't you need the DDP stuff for that? Because like,
it is that's a great question. So if you were running a single server that has multiple GPU nodes, you don't need the DDP. If you're running your training loop in multiple computers, these are independent boxes. They don't share memory, they don't share GPU. So they connect through the network. That's where the DDP handles all that synchronization.
okay, because like the PyTorch has like multi-node like code, right? And they use like DDP and stuff like that, and then local rank and stuff. So I was like, because you just did it in like 1 line basically. So I was curious, like, why? And it was just like you just plugged in the code without even having to do that. So,
Yes. So
crazy.
the reason for that is that it's all taken care automatically. So let's go here. There is a function that initializes the DDP.
Right there, like
Yeah.
inside
Yes.
the class trainer, yeah.
Yes. So when you use torch run, it'll set the rank for you. So depending on what's the computer, it'll assign a value of 0, 1, or whatever rank is there, and it is going to get it. So there's a function in which you can download it or read it. Yeah. hold on.
So does that mean we didn't have to like do this code and just done like srun in the HPC, like in the Slurm environment, and just ran it using torch run without even like writing this code?
No, you do need to write this code, but what you get is this parameter rank is filled in by torch run. So if you like pay attention carefully here, this is the entry point of the script. And then we are using the multi-processing module to span a new process, assign the main function as the entry point, but nowhere on the arguments we're specifying the rank. So when you run it through torch run, it already passes as the first argument what is the rank. And it does that by reading the environment from the Slurm environment. So you do need to do some special handling, like in this template example, but you don't have to go and orchestrate the launch of the processes yourself. Okay, so I want to show here. This is first on the interactive job. Now this is working, so you can see how the GPU it changes. So the value will change to 100% and so forth. So that means that this must be doing something already. Now, it's still waiting for allocation. I'm going to kill this because it might give me some space. Okay, so it ran a single GPU. Now let's wait for it to finish getting the allocation, and hopefully we'll see it running on two GPUs at the same time. Let's see what's the status. So I'm going to exit this. Okay. Now it's running. So we have these two nodes. Let's SSH into each. And when you use sbatch, you'll get a file that has the standard output there. So it'll take a little bit. So we may need to wait another 10 minutes for it to start running on the GPU because imagenet is huge, but it'll work. So if you can stay with me past the hour a few minutes, I'm gonna stay here. And but if not, then I will post all these materials into the website. So the way you can verify what's going on is that you can use the tail command. Here you can see that so how do you know that it's working in two nodes? You can see the duplicate warning messages. Like boop, it's a debug message, the debug print statement that I forgot to erase. But let's see a let's SSH into this. Okay, it is working here. So on this node, this is node 3. Like you can see how the memory is saturated, the GPU usage is being saturated. You're using less than half the memory. That means that we can still pump up the batch size a little bit. I don't know if the speed is going to change because we're close to 100% all the time. So we might just have hit the performance offered by the VM100. So this is a node 3. So let's go back and see what is the other node. And there you go. It is working as well with 100%. So great. So something else that it's important here. When you're running the HPC, you request ahead of time how much time do you want to use it. If you finish before, great. So you didn't burn the hours, but sometimes it's not going to be enough. So you want to save the checkpoints. In this template of code, you will have a save checkpoint hook in which we are saving into a file if and only if the rank is the first one. So we don't want to save the checkpoint twice, once for each worker. So GPU ID has to be equal to 0. If you trace back this parameter, is assigned through the rank. And I want to show you the output. So it is going through the way it's configured is going to do a single epoch. That is 1.2 million images. Since we have a batch of 128 images per pass, that's 5,005 steps. And the code estimates that it's going to run through the epoch in about 30 minutes, 30 to 37 minutes. It changes. So you can see how it varies. When you do it on a single GPU, so I wasn't able to show it to you, but this takes about an hour. So we have almost like a linear scaling. We don't have perfect linear scaling because when you do this distributed computing, you have to synchronization of the processes, and then you have to transfer the data back and forth through the gather and scatter constructs. That takes time, obviously. Like there are CPU cycles on doing all that, and it takes a toll. So that means that if we had 4 nodes, we wouldn't be running this in about 15 minutes. It would be probably closer to 18 or 20. And if we start scaling up, there's going to be a point in which we're going to spend more time doing synchronization than doing the actual compute. And that is just a fact of life. If you take any parallel computing class, that's going to be early on realization. If it wasn't that way, then the parallel computing folks wouldn't have any job because this could be trivial. But it is kind of an art, so you need to take into consideration those artifacts and those consequences. So yes, Jake. So thank you for joining.